All right, everybody, welcome to today's video. We're going to start talking a little bit more about applying quantum chemistry to molecular systems. Okay, so going beyond the hydrogen atom and such, we talked some about molecular orbital theory, and that will be kind of related to some of the things that we're going to be talking about today. And so we're going to first start talking about the variational principle. Okay. So as just a reminder, right, why we need approximations, why we need molecular orbital theory and other things like that to try to study molecules, right, and the electronic wave functions and energies of those molecules is because of the electron-electron repulsion, right? The fact that there's this this potential energy term that depends on the distance, right? R12 is the difference between the distance of R1 and R2, right? It's the distance between two electrons, right? And because of that, we can't separate our variables, can't solve this differential equation, okay? And so this is where the variation principle comes in, okay? So one of the wonderful things about trying to study molecular systems is being able to use this variational principle. It's a very simple thing, but it's a very elegant and very useful property of a quantum mechanical system, okay? And the variational principle states that if you pick an arbitrary wave function to calculate the lowest energy of your system, the value that you calculate is always greater than or equal to the exact value, okay? Right? So what that's saying, right, is if I guess some wave function for my system, okay, that my guess will always have an energy greater than the actual wave function, or equal to if I guess the true wave function, right? And so that gives me something that I can try to optimize, right? Try to minimize, right? If I know the better my guess, the lower my energy is going to be. That means I can try to improve my guess systematically, right, to lower the overall energy of my system, right? And I know if I'm getting a lower and lower energy, I know I must be getting closer and closer to the true value, right? To get the true wave function and the true energy for your system, okay? And that is a very key principle behind modeling molecules, right? Electronic structure theory, applying quantum mechanics to the electronic wave function for molecules is this variational principle, right? Right, that my guess wave function, right, will have some eigenvalue, right, some energy that is always greater than or equal to the exact, right? Now, often how we get, right, calculate this guess energy, right, right, is we calculate psi h psi, right? This is this E, right, my energy from like my guess wave function, that would be my guess energy, right, which is related with the integral of psi star guess h psi guess, right? This is like the type of integral you'd have to solve, right? And this is what's done in electronic structure theory calculations. Yeah. Right, and in principle, I can use the variation principle to study not just the lowest energy state, but higher energy states as well, okay? Now, it's a little trickier if you try to apply this to a higher energy state because, right, you want to make sure your guess doesn't somehow get your lower energy state wave function, right? And there's issues with converging to higher energy states when you try to optimize your guess and things like that. But we won't really focus on that. Here, we'll just assume we're applying the variational principle to calculate the lowest energy state, okay, ground state for a given molecule, right? And so, right, an example of trying to use this variational principle would be, say, let's say I have no idea what the wave function looks like for a particle in a box system, but I'm going to guess it looks something like this. This is my normalized wave function, right? My normalized guess for the particle in the box ground state wave function, right? For that ground state system, okay? And right, and so we can look: is this right, going to equal the true ground state energy, right, and how close is it? Okay, so given our guess, right, again, we want to solve for the expectation value of the energy, right, which is related to that integral of your guess wave function times Hamiltonian times the guess wave function, right? Our Hamiltonian for the particle in a box system is just the kinetic energy term, okay? And so this is the integral I'm trying to solve, right? So just rewriting the integral here in the slide, right? We're going to use our guess wave function and plug it in, okay? And so what I've done here is, right, I'm pulling out the constants, right, in front of these things, okay? Right, there's 3 negative signs. You'll overall have a negative, right? And then you'll get 30 over L times h bar squared over 2m. And then we have this integral that we have to simplify, okay? So to simplify that integral, first what I will do is apply this second derivative to x squared and x, right? Second derivative of x is just equal to 0. Second derivative of x squared is just equal to 2. And so this simplifies down, right, here to just 2l squared, okay? And then now I just, right, pull that 2l squared out, okay? Right, and just pull that out of the integral, and so I just have the integral of 0 to L of x squared over L minus x over L, okay? And so this final expression here, I just simplified the constants out front, okay? So now we take that integral from 0 to L, right? Integral of x squared is x cubed over 3. Integral of x squared over 2, okay? Evaluate these at L and 0, right? The times when you evaluate them at 0 is just going to equal 0, okay? And so you're going to get L cubed over 3L squared minus L squared over 2L, right? Simplifies down to L over 3 to minus L over 2. Find the common denominator and simplifying everything, I get the final energy term here, right? 5 h bar squared divided by ml squared. Right. So that is the energy of my guess wave function, right? We know the true energy, right, given here, or writing it in terms of h, right? We've also seen it as h squared n squared over 8ml squared, right? Okay, so right, using h instead of h bar, but here I have h bar, right? So plugging in n equals 1. And if you plug in for pi, what you'll get is 4.93 h bar squared over ml squared, okay? Right? And so this is a lower energy, right? This is the true value. Right, this is true value, okay? And that is lower than our guess value, right? Not by a lot, but it is, right? So our guess was actually not a half bad guess for this system, okay? Right? And so that is, right, kind of how you would use the variational principle, right, to kind of see how close are you to the true value, right? And in practice, what is done is instead I would have my wave function be written something like let's say it's 5x, right? And I have a similar guess where it's going to still be like an x squared over L minus x over L, right? But what I'm going to do here, okay, is I'm going to use the fact that, or I'm going to multiply this second term by saying alpha, okay? So I'm going to multiply this by alpha, right? And then what you can do is this thing kind of makes your wave function, right, not really just a function of x, but you can think of this as a function of x and this parameter alpha, okay? And then what you can do is you can vary alpha, so you can change alpha to try to minimize your energy, right? So if you were to like plot alpha versus the energy, right, you'd get some random curve or something like that, and there will be some optimal value of alpha that gives you the lowest energy, right, and that gives you your best guess wave function. And so that is how we use the variational principle to study molecules. And we'll talk more about that in a future video, right? But that's kind of the idea. So in the variational principle, I can vary a parameter to try to minimize my energy, which is getting me closer and closer to the true actual value. Okay, that is a very, very useful aspect in quantum mechanics, right? When studying molecular systems, is being able to use this variational principle.